My name is Takehiko, Tohoku University and Green Planet. I report anomalous excess heat generated by the interaction between nano-structured palladium nickel surface and D2H2 gas. First, new division devoted to condensed matter nuclear reaction has been established at the Research Center for Electron-Photon Science in Tohoku University last year. We don't have much experience on excess heat experiments. So we started excess heat experiments similar to Dr. Misno's experiments. So my report is contents is first is replication of Dr. Misno's experiments. And next section is high pressure and long-term experiments using gas circulation systems. I introduced easily Dr. Misno's experiments. This is schematics of Dr. Misno's experiments and his levels. And his experiment is, the key point is 3 points. First point is to produce palladium nickel nano-structured surface in the chambers using plasma discharge. And second is D2 and H2 gas introduce the chamber and is the heater up to some temperature keep heat observed anomalous excess heat generated. So we start experiment using similar device and producer from Dr. Misno's, and I will introduce our experiments next. This is the experiment apparatus. Apparatus is composed vacuum chambers and electrodes and heater and evacuation systems. This is palladium rod and this is ceramic heaters. And this photograph is chamber's photograph in stainless steel chamber and chamber volume is 7.5 liters. And this is heater and electrodes schematics. And this heater is ceramic heaters, 25 centimeters squares, and some cup is built in this ceramic heaters. So we can heater's temperature directly measured using this some cup signals. And palladium wire is winding this ceramic heaters and to connect to the high voltage. And the next palladium rod is set in this chambers, and this palladium rod connected high voltage. This is a photograph of the ceramic heaters and palladium rod is photograph. That is our chambers is electrodes. And next, this electrodes and ceramic heater, we around the nickel mesh, nickel mesh surrounding these electrodes. This is the center of the chambers. This is experimental apparatus photograph. Chamber is covered with thermal insulation material and aluminum foils, reduce the room temperature fluctuations. And this is setting the chamber's photograph. Now, procedure, I explained the procedure of experiments. First experiment is the reference runs, this is no activations and no nanostructures. Activation is experiment related, and this reference run is first experiment is heater and input and temperature measurement under a few pascals, but almost vacuum conditions. And the second experiment is introduced to these gas and temperature measurement. And this is the reference case. And the next activation treatment of palladium and nickel. First is glow discharge under argon gas. This experiment, next slide. And next to baking 100 to 700 degrees, and third step is these gas absorptions. So after activation treatments, we go foreground run with activated nanostructured palladium and nickel metals, and same experiments 1 and 1 and 2 and 2, and compared with the heater's temperatures and estimate excess heat. This is a procedure of the experiments. And this is activation process and fabrication of the nanostructured nickel and palladium surface. I performed two patterns discharge. First pattern is palladium rod connected to high voltage is minus high voltage, and argon gas introduced to the chambers and argon discharge in this chambers. So argon ion adapt to the palladium and palladium sputterings, and palladium sputtering particles disperse in the chambers. And next step is shaft is palladium wire connected to the plus high voltage. So next argon ions adapt to the nickel meshes. So nickel mesh sputters this argon ions, and nickel particles disperse in the chambers. So shaft 1 and shaft 2 discharge alternated repeated mixed palladium nickel and making nanostructures on the this heat ceramic heat on the ceramic heaters. It is a photograph after experiments. This is before ceramic heaters photograph. So this is silver light is palladium nickel nanoparticles. It's same image and zoom image is this. About 100 nanometer particle is fabricated. This is experiments. And this is reference data. This axis times and temperature and deuterium pressures and heater input bars. Heater input is 40 watts input. And first step is heater temperature is 7 degrees. And next is D2 gas introduced. Gas cooling is temperature is slow down. And foreground experiment is next. This pattern is 170 Pascal deuterium is loaded in the nanoparticle, and this time is gas evacuations, and same time is heater input. Heater power is input to the heater, and so 40 watt input. So heater temperature is rise up to the about 50 degrees up to the heater reference data. And so gas, next is introduced D2 gas is temperature is slowed to back, but its heater is temperature is rise. This is I think the heater is higher. And next is 7 watt input and same experiments. So this case is very large difference at 123 degrees, and this phase is 28 degrees. And so in our experiment, heater is covered with nanoparticles. So influence of the nanoparticles is influence of the radiation heat transfer. So we numerical calculation using estimation for radiation heat estimation using a console multi-physics. So this is experiment 1 and experiment 2. 5 degrees difference is this pattern, but the estimation emissivity of palladium nickel nanostructured material go down to 0.1. So about 50 degrees increase would be expected. So this case is difficult to exclude out the possibility of the radiation heat transfers. But on the other hand, 300 degree case, even though emissivity goes down to from 0.7 to 0.4, drastic change, but about 7 degrees increase would be expected. So difficult to explain it over 100 degrees increase, difficult to explain. So it is, we think this case is anomalous excess heat generated. So we want to do long-term high pressure experiments. So our experiment is, this case is gas desorption process is, this case is a batch experiment. And this case is a desorption process, but our experiment is gas input and evacuation same times do. So this gas is so expensive, but so it's difficult to high pressure and long-term experiment is difficult to perform. So high pressure and long-term experiment is we introduce this gas circulation system. This is circulation pump and using hydrogen filters. This is remove H2O hydrocarbon also etostra from T2 and H2 gas. So we circulate a very closed cycle. So we use long-term experiments. This is result of the T2 circulation experiments. And this is 100 kilopascal about 1 atoms experiments. Heater input is constant keep 20 watt keep, but heater temperature is gradually rising to the up to 2. And about 40, about 30 degrees up this. The experiment time is about 20 hours. We continues, but thermal equivalent is external environment is thermal equilibrium. This is chamber temperature. We set the thermocouple chamber walls 3 points. This is equilibrium. But chamber and outer environment is equilibrium, but only heater temperature is rise to phenomena. And next is hydrogen circulation experience. This former is D2, this is S2 experiments, and same this type 400 hours continues. So little time temperature up, and same as thermal equilibrium is external environment. So somewhat in this gas circulation experiment is some heater generation possible occurs. Conclusion: we tried to excess heat experiment similar to Mizuno experiments. We observed that heater temperature was higher as reference non-fabrication nanostructures. In this case, 7 watt input heater temperature is higher, 120 plus than reference and excess heat is. Next, we have to add to gas circulation system to this node experiment and try to perform high pressure and long-term experiment. And we have observed phenomenon which in the heater temperature is rise slowly. The phenomenon is suggested anomalous excess heat. There is need for more detailed investigation. And special thanks to Dr. Takehiko and Professor Hashizue, Professor Yuasa, and Mr. Hideki Yoshino and Mr. Hattori. Mr. Hattori, thank you.